Yes, so it took us 15 minutes to get this on. That's kind of embarrassing because this is approximately the first observational project that I have been sort of setting up. And so observers are usually presumed to be better at handling machinery. What I want to talk about is... So what I want to talk about is some last results. We are finishing up a paper that is the result of some years of a survey that we have been setting up, wherein systematically we study the properties of galaxies in the interior of voids. This is a multi-wavelength study involving wavelengths running from the optical to the infrared. Till in particular, in this case, I also will talk about radio 21 centimeter line observations with the Westerbork radio telescope. So basically what we do is we take the Sloan Digital Sky Survey. This is not a Sloan Digital Sky Survey, but in the Sloan Digital Sky Survey we have, of course, a spatial distribution of galaxies. And we are particularly interested in the galaxies that you will find in the interior regions of the voids. Why? Well, they are interesting regions because supposedly they're pretty pristine. So the processes that take place there do not involve a lot of interactions, we thought. So that galaxies over there are, you know, sort of calmly evolving and would tell us a lot about how galaxies unaffected would have evolved. The issue involved both selecting these void galaxies and secondly setting up the program and getting the observing time to basically study these guys. The project basically started first with the Sloan Digital Sky Survey. From the Sloan Digital Sky Survey, we will make maps, density maps, in a particular way. And from these density maps, we subsequently use a technique to identify voids, which, if you have heard the previous talks by Dimitri and Christoph, is very much related to what they are doing, called watershed technique. And then we are assured, by keeping the cosmic web structure that is around in the Sloan Digital Sky Survey, we are assured to find the galaxies that are really in the interior, in the most inner areas of the voids. Here you have a selection of them. By now we have a selection of around 60 of these galaxies. As you see, most of them are pretty blue and little dots. That's a very typical void galaxy. A few of them are early type, and we will see what some of these guys' properties are. Towards the end, I will show two of these guys who are really surprising properties. We will kind of base, it's not very desolate and not very empty in those areas. It's very active actually in the void interior. Well, this is a big project. It's involving a lot of observing time, and if you want to observing time, you need a lot of people. So here are some of the people involved in this. This is both graduate students, postdocs, as well as a couple of other people running around. If you really want to know the people who did most of the work, Catherine Stanonik is the one who has been doing by far most of the work, and Erwin Platen. And here's Miguel Aragon, and our newest student, Butcher Bedu, who's doing in particular the observation or the optical and the near-infrared side of things. So, what questions are we trying to answer? First of the questions is, are void galaxies intrinsically different? That's an important question. There are various claims that they are intrinsically different from normal galaxies. The question is, are they really? Well, we will see they are really indeed bluer. They are fainter, indeed. They are much more active at forming stars. But we will see that most of the time they are pretty much standard. They pretty much fit on the standard magnitude color relations, etc. The other thing that we particularly wanted to address, of course, when a galaxy is forming, it's not only the galaxy itself, but in particular, you want to know where the gas is coming from and what the gas is doing. That's where our interest comes from of observing these things in H1, looking at their H1 gas layers. So we want to know, is their H1 gas layer different? Does it have a different morphology? Do we see evidence of gas accretion? And when there is evidence of the gas accretion, in what form may it come? One other aspect that, of course, is going along is the claim that there is a shortage of dwarf galaxies in voids, the so-called void phenomenon forwarded by Jim Peebles. Is this really true, or can we find them in a particular way? And finally, we're also interested in tracing substructure in voids here and there, because in a hierarchical scenario of structure formation, you do expect that. Let me skip that. Now, the project involves a sample of 60 carefully selected galaxies. Carefully selected means not by their intrinsic properties whatsoever. Purely geometrically, purely on the basis of where they are situated. Subsequently, the campaign involves a lot of radio time, both Westerbork and VLA time, mapping their spatial gas distribution, studying their kinematics. We've also have the data of all of them with Galaxy ultraviolet. We have started near infrared J and K imaging. We only have up to now a few of these guys, some of them with the old Palomar telescope, so that was pretty interesting. We have H-alpha imaging, very deep B and R imaging, and optical spectroscopy to study the kinematics in the interior of these galaxies. Skip this. Now, of course, one of the questions is, how do these galaxies relate to the underlying matter distribution? We don't know really, but sometimes the simulations give us a guide. Here you see a certain section from the Millennium simulation, a large-scale dark matter distribution with blue dots, semi-analytical modeled distribution of galaxies. So even if you can find some of the galaxies in the interior, you see it with blue dots, you see that usually you hope that they are tracing some tenuous structure within these faults. The question is, do we really find something like that? Can we find filaments in these faults by looking at this? Now, first, what strategy did we use to trace these galaxies? It's a geometric selection, independent of the intrinsic galaxy properties, except that we, of course, used the selection criteria of Sloan. That is, the apparent magnitude had to be smaller than 70.77, and we restrained ourselves to 0.01 to 0.025 in redshift. This galaxy distribution, spatial galaxy distribution, is subsequently turned into a map, a density map. I will show you that soon, with a technique that we developed over the years by ourselves, the so-called Dubinski tessellation field estimator, which guarantees that the anisotropic and hierarchical structure intrinsically present in the galaxy distribution stays there, not with any smoothing involved. We don't want that, because we don't want only to pick up round voids. It should also be able to find galaxies, for example, in ellipsoidal or elongated voids. You don't want to destroy this with filtering. Subsequently, on top of that density field, we used so-called watershed void finder to find the galaxies, or to find the voids. And then within the voids that are finally traced, we only select the galaxies that are in the interior where the underdensity is lower than minus 0.5. Right? So you're really at the center of these guys. Now, how does this look like? Well, let me skip this. This is just to give you an impression what this DGB method does. Here you see an embodied simulation processed by this density reconstruction procedure based on the so-called Dubinski tessellations. And you see all the filamentary sheet-like structures that we find in the Galaxies distribution remains, as it does the hierarchical structure that we find in there. So if you zoom in there, you still find the structure. It's not an extra step, it's all in the same map. Potentially you can do the same for the velocity distribution, but this was only for an embodied simulation. What we're interested in is this map. Now, like I said, it keeps the structure that is in there, the anisotropic structure in the hierarchical distribution. Subsequently, you should see this density map as a landscape. And here you see basically the density distribution translated in a landscape. And on top of this landscape, you see ridges. So these ridges are the so-called watershed transform. And what this watershed transform basically does is identify the basins in this landscape. So you see this is a basin, that's a void, and here you're really in the interior of a void. So the question is, can I find it in this way? Now, this procedure is, of course, it's a procedure that is quite akin to the Dutch people, because basically you take a landscape like that, and why it's called watershed? Well, you take a water level, and you let the water level come up, and the landscape gradually gets flooded.
We do it the other way around.
These days, not anymore. So you can see that the landscape basically comes up, and gradually, as the landscape comes up, you start to see that it segments basically the landscape. Right? Only three. Oh, gee, then I have to hurry up. Okay, so this is what we did. We basically identified the segments of the landscape, and then in the segments of the landscape, we identified the galaxies. So let me rush up. Okay, so this is what the observational situation is. Here you see basically the Sloan digital sky survey on the sky. Here is one of the void galaxies. Here's the density map where we superimposed the galaxies. And you see that's one of our guys. Here you see this watershed transform, and you see it's really right in the center. Right? So we had some 60 of these guys. We had a lot of other things. We had to ensure that no fingers of God were involved and all these kinds of things. But basically that's what it is. Now, we started with a pilot sample of 15 galaxies. Here you have the 15. The most interesting thing I can already say is this guy, Void 03. Void 10 is an interesting one too, but in view of the time, I will basically continue by walking down. Here is Void 03. Now surrounded, this is the galaxy distribution from Sloan spatially, and that's where it is in the interior of the void. Now, where do you find these galaxies? Here is the color magnitude diagram. The triangles are our void galaxies. These other points were previous selected void galaxies or previous studies. And you see it's quite different. You really have to be here at the bottom of the blue cloud. That's where they are. Right? If you want to compare it in the Sloan map, basically the red triangles, or in the Sloan survey, these are all the galaxies that fulfill the requirements. And you see the pilot sample is really up there. Right? So that's what you get. Notice, by the way, that the galaxies in our sample, therefore, completely fall on the regular distribution of galaxies. There's no indication for them being that big. They're blue, faint. They're very active at forming stars. And we can show you that with, for example, some of the observations. So we used a lot of hours on the Westport radio telescope, where all these things were observed with a program involving these parameters. And here are some of the guys. This is one of the most regular ones. We call it the flapping void galaxy. It's pretty large. It has a dynamical mass of 6 times 10 to the 10 solar masses, a hydrogen mass of 38 times 10 to the 8, and you see it has a beautiful rotational pattern. So it's a beautiful rotating disk. But not this one. This one is centered here. This was the prime target galaxy, but you see there's one here, a companion, and there's a companion over there. It turns out that a lot of these guys have companions. And so they're not isolated in that sense whatsoever. You see, it's here allocated along a certain filamentary or elongated structure. This is some of the choices. So here you see the brightness distribution, the radial brightness. This is basically the kinematic distribution. And here you see the velocity against the angular offset, from which you can see whether they rotate like a disk or not. What kind of properties? Well, let me go on. I had a lot of stuff to show. I was clearly optimistic. One of the properties in which they differ is they are smaller than regular. So here you see the optical size of these guys as a function of their apparent magnitude, and you see they're all smaller. That's the one thing in which they all differ. That's the most significant difference of these void galaxies. They are not different in terms of their surface density profile. They are also not different in their star formation properties, except that at the very lowest end, you see that there is more star formation per hydrogen mass than a regular galaxy is doing. That's one of the differences that we found. So they follow in general the trend of that the hydrogen mass per luminosity is basically following of the regular galaxies, so they're not different in that sense. We don't see any trend of hydrogen mass over luminosity with density. And particularly interesting for us was whether we could find any difference in the Tully-Fisher relation. And they don't. They fit very nicely the baryon-Tully-Fisher relation. And in this sense, it's very important that our limit, lower limit of total mass was 2 times 10 to the 9 solar masses, just above the limit where Hooft et al. Predicted that the UV background would affect basically the baryon content of these dwarf galaxies. So, one more thing. Okay. Void 03. Void 03 turns out to lie in between 2 voids. It's one of the most isolated galaxies in the UGC catalog. Its nearest neighbor is 4 megaparsecs away. Right? So, what turns out? This guy has a polar ring. Here you see its beautiful rotation pattern, but that's the central galaxy, it's perpendicular to it. Within the ring, there is no star to be found whatsoever. That's strange. Particularly strange because the central galaxy has a disk-like appearance. The regular theory says that the polar ring galaxies are the result of a merging event. But in that case, you would expect that the central galaxy would not be disk-like. So what's going on here? A polar ring without any stars in it. Could it be this? This is just a question. Cold accretion as a result of the outflow of matter from the 2 voids in between which it is located. That's a question to the simulators to answer. I will stop here with this result because I think this is the neatest specimen that we have up till now. Void 214 we are reducing at the moment, and void 214 is a filament of 3 galaxies. One of them, void 214, being the target galaxy. Also that is a ring galaxy, or a galaxy wrapped in tidal streams, and all 3 of them are embedded in a hydrogen cloud, which is very elongated. The only conclusion can be is that the galaxy, or the voids, are not desolate places whatsoever, that the life of a void galaxy is not boring, that they're very active, and that they are indeed very nice laboratories to test several theories of galaxy formation. And, well, this was primarily the first report on this project, and this project will certainly continue over the coming years, and I will certainly keep you updated on this. Thank you.
We just have one question, and there we go.
You said very elongate what the roughly ratio of X.
It's more than 10 to 1.
And what is the long dimension?
The long dimension is around a megaparsec actually, the cloud. So there's 3 galaxies embedded in something a stretch of around a megaparsec.
How about this plot here? The galaxy is like a kiloparsec, and the H2 region?
Yes. This galaxy is around, the whole thing is around 10 kiloparsecs.
Do you have dark matter rotation curves for?
What?
Do you have dark matter rotation curves for any of these void galaxies?
No. Well, we do have the hydrogen rotation curves, and for most of them, we indeed have. If you saw this velocity position map, you really see that we are getting into the flat rotation part of the curve. So for example, the Tully-Fisher relation, we have quite good estimates of the overall dark matter mass.
Okay, maybe
You call it?
keep Christoph back in there.
Am I right to say that you found less variation in these galaxies than you were initially expecting in terms of colors and things? Or
We found less.
you found less than you were initially expecting? Is that
Well, we found less difference with the regular galaxies, so they're not really different.
because we made just a much less interesting analysis, but doing this on simulations. And our preconception was that we were expecting to find differences, and we didn't as well.
Okay.
Real quick,
Just a quick question about so the most exciting is really interesting. The most exciting stuff is that at a given luminosity they seem to be smaller than the galaxies the same luminosity.
Yes. Yes.
But the size is something tricky to measure because galaxies don't have a size as such. So is that there are no systematics in that? I mean, you measure sizes exactly the same way inside and outside.
It's determined from the Sloan images here, and you saw the differences with the other Sloan images and the regular ones. So the line, it's from the same sample. So the line was the median of the Sloan sample, and these were estimated from the Sloan images of these galaxies.
Okay, so it's the same thing.
It's the
from
same. It's
database.
the same thing.
Whoa. What do you make of it? Less angular momentum. Pure tidal thoughts.
Okay, so now we're going to hear about the tank passive Andromeda and Triangle from Larry.
Okay, so this talk and the one that follows by John will describe an observational program called PANDAS and some of the simulation and theoretical work that we've been doing in support of this program. The goal of the PANDAS project is to map out the stellar content around M31 and M33 and to use these observations to study galaxy formation and hierarchical clustering in the local environment. So I'll begin by describing the PANDAS project, and then say a little bit about the tools that we're using on the simulation side of the collaboration, and then John will pick up the story and describe, I think, what is one of the more interesting ideas to come out of at least the first year of the PANDAS survey, that M31 and M33 have had a recent encounter. So, not surprisingly, M31 has played a role, I think, in many of the major discoveries in galactic astronomy over the last century or even longer. Its close proximity and similarity to the Milky Way make it obviously one of the most studied galaxies. In terms of its stellar content, one thinks of surface brightness maps of the galaxy, and from these surface brightness maps, it's traditional to make cuts in the surface brightness profile, cuts to make surface brightness profiles. So I'll just advertise an upcoming paper with Stefan Coteau, Mike McDonald, and others to look at the surface brightness profile of M31 in some detail and carry out a disk bulge decomposition and also look for the nuclear component and faint component as well. M31 was, of course, the first galaxy in which the significance of a flat rotation curve was recognized, the famous paper studied by Rubin and Ford, the first evidence for dark matter halos around spiral galaxies. And I think aside from the Milky Way, it's the most studied galaxy in terms of the use of kinematic tracers to map out the distribution of dark matter and place constraints on the total mass of the galaxy at large radii. In the upper left is a scatter plot of the globular cluster system of M31 out to 100 kiloparsecs. And on the right is a map of the satellite distribution of M31 all the way out to M32, and so now out to an area in projection of about 200 kiloparsecs. And one of the goals of the PANDAS survey is to find more globular clusters and more satellites, and in fact, in just the first year we've done that. So I think a significant discovery was made by Annette Ferguson and collaborators, actually the nucleus of the PANDAS collaboration. And their goal is to map out the stellar content at large radii of this galaxy. Essentially, they're counting red giant branch stars and then inferring the total stellar content from the RGB counts. This is a project, type of observation, I think, that has the flavor of a particle physics experiment, in that you make maps of all of the point sources in the different fields of view of your survey, and then dig out a signal, in this case the RGB stars, from a large background being galactic disk stars or galactic halo stars, or misidentified point sources that are really galaxies. And so you have this enormous number of background objects, and then one is digging out this very small signal, essentially by finding the right region in the color magnitude diagram. So this brings us to the PANDAS survey, PANDAS standing for Pan-Andromeda Archaeological Survey. Alan McConaughey, the principal investigator of this, is quite proud of that acronym, inspired acronym by his own account. It's a 3-year program at the CFHT, designed again to explore the global stellar content of these two galaxies. About 300 square degrees is the total survey area. It's a project that includes collaborators from Canada, the US, Europe, and Australia, and a number of people here at this meeting. I think Julio is supposed to arrive, Aaron Goddard, and John and myself. The first year survey revealed a number of interesting results, some of which were known previously. So here's this giant stream that one sees in the south around Andromeda. So that's a stream of stars, as well as an arc, and then various other features, some new in the first year of the PANDAS survey, and others known before. And the general working hypothesis is that these objects are the tidal debris of satellites that have been disrupted by the gravitational field of M31. One of the other discoveries, though, was that M33 has a stellar feature of its own, both to the north and to the south. And the working hypothesis of this is that it's actually stars dislodged from the disk of M33 during a recent encounter with M31. So here's a close-up of the M33 region, and you see a nice S-like pattern in this extended stellar feature around M33. And in fact, it seems to roughly correspond with the H1 warp. So M33 is known to have a large H1 warp, which has similar morphology. Prior to the PANDAS survey, M33 was thought to have a fairly axisymmetric, pristine pinwheel stellar disk. And we now know that the stellar distribution has this extended feature. And so we think we found the stellar counterpart to the H1 warp of M33. As well, there appears to be a bridge of H1 gas between the two galaxies. This was interpreted by Braun and Hilker as a cosmic web, but I think, and John may talk about this a bit more, that this may just be the debris from a recent encounter of these two galaxies, not simply as grand as a cosmic web. Now here's the second year of the PANDAS survey. This is unpublished, but shown at a collaboration meeting and now at various conferences. And you see this beautiful faint arc-like structure here, a number of other arcs, and then perhaps hints of a stellar bridge connecting the two galaxies, and a satellite galaxy here that was known before, but it appears to be tidally disrupted. And so there's all sorts of interesting features in this map and neat problems for simulation.
Is the other one at the same distance?
The two galaxies are at roughly the same distance. So they're about 200 kiloparsecs apart in projection. And
two little galaxies.
The two little galaxies, I'm not sure offhand. But one of them is quite clearly has this disruption in it.
What fraction of the total mass is in all these features?
I think it's tiny. Yeah, I mean these are very faint, again very faint features. You can see a very large range. M33 is
M32.
M32
is buried in
I think it's buried in the magenta.
It's much closer.
Okay, so let me say a few words about one of the tools that we're using to set up simulations to study what's going on in this local environment. It's appropriate to talk about that this is a code called Galactics for galactic initial conditions, and appropriate because it was first developed by Conrad Kakin and John when Conrad was a postdoc here and John was a graduate student, and then we picked it up and after you were a graduate student. You met when you were a graduate student. So there was a CITA. CITA was involved. And so picked up and refined and extended in a variety of ways over the past few years. It's a code that can set up a pristine equilibrium disk galaxy with a centrally concentrated stellar bulge, a thin disk, and an extended halo. So it yields axisymmetric equilibrium models useful for the study of galactic dynamics. It's meant really to be something complementary to ab initio studies of galaxy formation. And so rather than try to build galaxies from cosmological, from the beginning, this code is meant to be something to study individual galaxies in detail, bar formation, or the merging of galaxies and so forth. It also, I think, provides a useful template for the interpretation of a wide range of observations. It's a model that's specified in terms of phase space distribution functions, where the only physics is the epicycle approximation and setting up the disk. This is something that can be compared with other, I think, popularly used models of disk galaxies that you find in the literature, where the assumption is that the local velocity distribution is Gaussian. And so in those cases, one is basing the model on Jean's equations rather than Jean's theorem. Those models tend to relax to a different state. They're not true equilibrium models. And so I think for setting up sort of pristine initial conditions and then studying things like bar formation and so forth, these are probably more accurate or appropriate models. I can say a few words, I'm probably running a bit long, but I'll say a few words about how the code is set up. One can choose as the user of the code target density and potential for the bulge and halo, and a density law for the disk. Build the distribution function for the halo and the bulge from Abel transform, and then solve Poisson's equation iteratively, 3 minutes, okay? In full axisymmetry. So the details obviously appropriate for a longer talk. One of the things that we've worked hard on is to work on a way of tuning the models to a particular galaxy. The original Finken and Dubinski paper, it was essentially pi by I. You would tune the different parameters to get the rotation curve. A rotation curve is something that was desired. But by far the most, I think the most useful way is to apply Bayesian statistics and Markov chain Monte Carlo. So take whatever data you have for a particular galaxy, develop some figure of merit, and then apply these techniques, and you can get a whole suite of models that fit the observational data. And so a single Markov chain, Monte Carlo Markov chain run, then provides the full probability distribution function in the model parameter space given the observational constraints. So we've done this for the Milky Way, applying similar observational constraints to that were used in a well-known paper by Bannon and Vinny. So things like the Oort constant, the rotation curve, luminosity and dispersion for the bulge, and so forth, and build up a suite of models for the Milky Way. And then you can use those to study things like the susceptibility to bar formation. So one can project all of these models onto, say, a two-parameter plane where the two parameters are the parameters that we think control the susceptibility to bar formation. A parameter called dubbed x, which essentially tells us how self-gravitating the disk is. When x is large, the disk is essentially test particles and not susceptible to bar formation. When x is small, you have a self-gravitating disk, and it quickly forms a bar. Q is the usual Toomre parameter, the temperature of the disk, which again controls how susceptible it is to bar formation. So one can project these models onto this two-dimensional plane, and then take some selection of those models and simulate them. And again, models down here should be susceptible to bar formation. They should be highly unstable. Models up there should be quite stable. And so I'll show this movie as Norm stands up and gets ready to pull me off. This is this grid then of Milky Way models. So all of these models fit the observational data. Yet some of them are quite unstable to the formation of bars. Others will take a few billion years to form a bar. So you can see the instability sweep across this diagram in this way. So this is just one of the uses of the Galactics code and Galactics models that we found. The code is available to anyone interested in their own galactic dynamics type investigations. So as a final lead-in to John's talk, we applied these techniques to build models for M33 and M31. Then John will describe how we used these models and did a search of orbits and so forth to study the interaction hypothesis. And let me just close by advertising two posters on related ideas. One by Nathan Degg, a graduate student at Queens, looking at models of the Milky Way and the Sagittarius stream. Another by Dan Foreman-Mackey, taking a look at the dynamical tracers of M31 and constraining the mass of the M31. So I'll stop there.
We have time for some questions. Scott?
So the structure that you see in that dramatic image is very impressive. But lots of people have taken images, wide field images of areas not close to M31 that also sort of show structure. How do you know that all those filaments and things that you see are associated with M31, with the M31 group rather than with their own halo?
Some of them, I guess, seem sort of obvious. I mean, the giant stream, points right back to the galaxy. One can. What's that?
Why do I not trust you?
One can. Yeah, sure.
Okay, so yeah, so I'll carry on with this discussion of Canada's result. So the one thing that we've been focusing on is this observation of this fluff, of these extension of stars around M33. So I'm going to discuss our attempt at modeling that process and also discuss how it might tell us something about the dynamics of the local group. So here's the film credits. The bold-faced people are the ones that I've been working with directly. I'm like the best boy, or he's like a gaffer or something. Okay, so basically there's a lot of issues related to galaxy formation in the local group. I'm just going to focus on, in this 10-minute talk, on the orbital dynamics of the local group, and maybe see if we can tell us how much dark matter is there and how it is distributed. So I'm also an amateur astronomer, so I like, so if you can see M31 in the Andromeda, constellation Andromeda. The lower right in the constellation Triangulum is M33. They're about 15 degrees apart on the sky. There's the Triangulum, but what's neat about Triangulum is actually it's a perfect model of the local group of galaxies. So the local Triangulum, the scale of the triangle is almost perfect within the errors. And even the magnitudes of the stars are pretty close. So basically there's these three galaxies, Milky Way and 31, which are comparable in luminosity, and then there's M33, which is down by a factor of 10 compared to them. But the geometry of the triangle suggests that M33 is a satellite of M31, and that's the way sort of we talk about it in this study. And so there's a long history of trying to understand the dynamics of local groups. So there's a famous timing argument, which is the second argument for a bit of observational evidence for dark matter after Zwicky's observations of velocity dispersion in galaxy clusters. And basically, it's a solution of the two-body problem for the local group with the assumption that so we know the relative distance, we know the relative velocity, radial component anyway. And if we assume the epoch of the orbit is the age of the universe, so they sort of laboring close together since they're falling apart, and now falling back together again. So the clue is that they're falling back together again, rather than expanding with Hubble expansion. So that suggests we're back. Use those, you can solve the two-body problem and determine a large mass. So here's a little table for different assumptions of eccentricity. Also, some other data in the table are just the closeness of the next pericenter, a prediction of what the transverse velocity should be for M31, as well as the time to the next pericenter or collision. And so, interestingly, that time scale is about 3 billion years or so. But the other prediction is that there's a lot of mass, and so that's sort of, this is maybe 4 or 5 times 10 to the 12 solar masses. The question is this argument robust? Is there really that much mass out there, etc.? Those are the questions. So a lot of people have studied this. I'm not going to review all of the report, but there's been a lot of people thinking about it in terms of galaxy formation and the boundary conditions of the formation of the local group, whether or not tidal torques are responsible for the local, the alignment of the disks and the dynamics of the orbit. So the big question, sort of visual question, is like, what is rho? Can we learn something about the density from orbital dynamics? So nicely, orbits sketch out the letter rho. Yeah. So here was our first. So as I was saying, we tried to model this fluff around M33 as some kind of tidal disturbance. So this was a plausibility calculation, basically, that we did. Just tried to found an orbit which seemed reasonable, which would have a close interaction and see if we could reproduce some aspect or some properties of that disturbed looking disk seen in pandas. So in this particular case, which is not necessarily a unique or definitive case, M33 flies by M31, disturbs it slightly, flies out to some apicenter of around 260 kiloparsecs or so, and then falls back in, and then ends up where it is today, about 200 kiloparsecs. Okay, and that's the constraint. Well, I'll talk about all the constraints on that orbit. It's not just made up orbit. There's a bunch of constraints. So in this particular case, the M33 falls from behind M31 towards us, basically around the front, and then curves around. We also we check. So I'll show you some close-ups of the disturbed disk. We also checked the hypothesis that maybe that disturbance was just the stellar halo of M33 being disturbed. But if you set up a stellar halo or set a test particle representing the stellar halo around M33, it's kind of too amorphous and doesn't show that nice alignment with the disk, so we don't really believe that hypothesis. Just zooming in, so. So I'll talk about, I'll just go to the next slide. So the summary slide was this, basically. Okay, you can set up an orbit that disturbs M33 without any problems. Now the question is it look good, look right? Well, yeah, you can get sort of an extension, maybe not as extended as we observed. One bonus was you can produce a warped disk. So, as Larry mentioned, M33 is long known how this gaseous work. And as I'll show you, most of the models that we've been trying lately produce a work with the right sense and the right sort of kinematics. So it's very compelling. But is it unique? And what else can we learn from this kind of stuff? So this is just a summary slide. Looks like M33 is heavily disturbed. Other people actually suggested that this might be going on, Becky in particular, in reference to the M31, M33 gas group. How can we use this information? Well, so I like building models. So with Larry's recent version of the Galactics code, we tend to construct a fully self-consistent setup of the M31 and M33 system with the eventual goal of adding the Milky Way to make that triangular. So what are the constraints? Well, we know the positions of the galaxies. We know the heliocentric radial velocities. We actually know the M33 proper motion, which is quite remarkable. But for the moment, there's no M31 proper motion. Other uncertainties with which things that we want to modify and change in the model to see what happens are the extent of the dark halos, extent of the stellar disks, and all of the various errors. So you can set up a big, you can use these methods to build galaxies. As Larry said, here are the two models that we've used, which are basic, they are good representations of M31 and M33. Yeah, you'll notice they have fairly low mass disks, and that was sort of intentional because we didn't want to excite bars, because both of those galaxies are known not to be too strongly barred. So that's another thing. Another trick we used is we actually sampled the disk with oversampled the number of particles in the other parts of the disk, so we can resolve the kinematics, even if I won't go into technical details. So it's a multi-mass model. We also chose 3 different models of M31, sort of one that represents a standard W-type prediction for the halo of M31, and other ones that have truncated halos. And there's a work distance prediction and the comparison. But all the models agree perfectly well within the observed within the disk. And so to do this kind of modeling, you also need to calculate a lot of orbits, test orbits. And unfortunately, dynamical friction is actually an important effect, so you have to incorporate it into these orbital test orbital calculations. So the trick we did was we would run simulations and orbit calculations, and then calibrate the Chandrasekhar formula coefficients to get matches, reasonable matches. And that was the way we built large families of orbits to check for consistency. There's the observations we've seen. This is what we're trying to reproduce. sort of roughly a 40 kiloparsec extent. Maybe 1% of the luminosity of M33 is in this faint extension. And there's this alignment of glass growth. These are all the things you want to reproduce in the model. I've got to get to the end here. Okay. So these are just old models. Larry showed you this stuff. There's the velocity field. That's another thing we want to reproduce. So here's just a recent higher resolution model which is going up by a factor of 10 from the original paper we did, showing M33 with all these zillions of particles in the outer region. But what I want to show you here is that M31 actually responds significantly to the passage as well. And the time scale is about 3 billion years ago for this passage in many of the models we were studying. So there might, well, M31 is known to look slightly warped and disturbed. So maybe this is an explanation. The M33 model, you'll see here's, I've just overlaid the optical image of M3, roughly this scale, on top of our in-body simulation. Just to show you that we're just trying to trace the kinematics in the outer disk sort of to represent gas or faint stars. And this is just a fairly high resolution model. So you get a beautifully tightly excited spiral structure from the interaction. And then you get this sort of broad extension, which kind of winds up. And we're hoping, if we do many models, we'll find, the one that looks exactly like M33. Haven't found it yet. Done a few dozen models with a exact match, but that's the goal. But this is just sort of our typical. Well, this is sort of our best kind of resolution that we can achieve right now. So you can look at these things. So if you look at it, John, so you see this nice warping feature, which is seen in the gas, right? I'm running out of time. I'm not going to go through all this, but basically we can do a Bayesian analysis of all the orbits, of all the possible orbits, and find the best fits. And we can actually estimate the proper motion of M31 based on this analysis. Okay. And we're getting solutions which show, well, for different mass models, fairly small values for the proper motion, which imply a nearly radial orbit near the head-on collision. Okay, so it's actually a prediction, and I understand that there are people who are close to making sort of these coarse measurements of the proper motion of M31. So hopefully we can use those measurements with this kind of modeling to constrain what kind of mass there is in M31. Okay, so here's just a picture of the distribution of orbits from different planes to give you an idea of what it looks like. So these are like all the orbits from 2 sigma of these within the 2 sigma configure of this analysis. Okay, and when you overlay them on pandas, you can type in other data, you can try to see if they match up with any features like the gas bridge or whatever, or other things going on in M30 in the M31 and M33 system. Okay. Anyway, I go on forever, but there's all kinds of detailed quantitative things you can do to compare these models to the algorithm.